Good morning. Um, I'd like you all to imagine you're walking down the street and you come up to a casino. There's a big flashing dollar sign on top, and you reach into your pocket and you feel a little money floating around in there. You're feeling kind of lucky and you're thinking, maybe I'm going to go in there and I'm going to make some money. So you walk into the casino and you are confronted with several different games that you can play. Specifically, there are three different games that you are allowed to play. Game number one is we flip a fair coin, and what we mean by fair is that the probability of heads is equal to the probability of tails, and each one of those is one half. Game number two is we are given a fair die. A die is something that has six sides on it, and you roll it. We note that it's fair, which means that the probability of all of the six possible outcomes are equally likely. So the probability of a one or a two or a three, four, five, or six, each one of those is one sixth. The third game that we can play is we can flip an unfair coin. And what it means by unfair is that it's a weighted coin, and we can see by the probabilities that have been specified up here. If the probability of flipping it and getting a head is 15 out of 16, that's pretty good odds, and the probability of flipping it and getting a tail is 1/16. So the way that this casino works is you are permitted to pick whichever game you want. And then what you do is you have to bet on a specific outcome. So for example, I could say I want to play game one and I'm going to bet $1 on the outcome being heads. I could play game two and I could bet on the outcome being a four. I could bet on game three, and I could bet on the outcome being a heads. If I bet $1 and I'm correct, I win $1. Otherwise, I lose $1. So the question down here at the bottom, part of it's blocked here, is which one of these three games would you pick and what would you bet on? Now, that seems like a fairly obvious answer here, but the goal here is that I want to be able to quantify why it is, and we know that the answer already is we would probably bet on game three. Can we mathematically give a precise reason for that? And that introduces this notion of what's called entropy. Entropy is a term that chemists and physicists use a lot. Entropy is a measure of randomness, or in other words, it's looking for a lack of order. Um, so the idea that game three, where the probability of heads is 15/16 and the probability of tails is 1/16, it would seem that is probably the least random of the three games. Okay. Um, on the other hand, game number two, which was rolling the die, and there were one of six possible outcomes, each one of them equally likely, it would seem that had the most randomness. And game number one, the idea of flipping a fair coin, probability of heads is a half, probability of tails is a head, that seemed that it would be somewhere in the middle. Now, physicists have always used the letter H to represent entropy. Somehow entropy here became entrop. So one thing that should be obvious to us at this point is that the entropy of game three is less than or equal to the entropy of game one, is less than or equal to the entropy of game two. So our goal at this point now is can we somehow translate these things into actual numbers? And the answer is yes. Okay, so it gets a little bit scary here, but I promise it's going to clean up. Um, I know when everyone starts talking about logarithms, people get very nervous, but I beg your indulgence. And if you just wait a couple of minutes and follow this through, you're going to see that aren't that bad. So I say, let's consider an experiment that has n possible outcomes. So in game one, there were two possible outcomes, heads or tails. In game number two, there were six possible outcomes, um, one, two, three, four, five, and six. And I said, let's call p sub I the probability of the ith outcome. So the one thing here that I hope you would all realize is that if I sum up all of the probabilities, they sum up to one. If they don't sum up to one, then we haven't properly defined the probabilities for this experiment. Now, what I want to do is I want to define the entropy of this. So I have H of P1 all the way through Pn, and then we get to this extremely ugly looking formula here. Okay? Minus summation over I, P sub I, log P sub I. Something that's important here, and we'll return to this in a second, we are talking about log base 2. That's very, very important. And again, if you're looking at this right now and you're feeling a little bit uneasy, that's okay. I hope this is going to clean up, like I said, in about 5 minutes. So I say, scary. So I say, please be patient. So the first thing I want you to recall, or maybe you don't recall it, a property of logarithms. If I say minus log of p, that's like taking whatever's in front here and moving it up here to the exponent. So there's actually a minus 1 in front of the log here. So that makes minus log of p is the same thing as saying log of p to the minus 1. And remember, p to the minus 1 is just the same thing as 1 over p. So keep this in mind, and let's go back to our original equation. So this was our original equation right over here, this minus summation over I, p sub I, log p sub I. So what I do is I bring the minus sign over to the p sub I over here. And now what I do is I convert it over here to its reciprocal. So this is the formula right over here, this one that I just underlined. That's the one that I'm most comfortable with. So let's look at a couple of things here, and now is where I hope it starts to clean up a little bit. If you want to consider the entropy of game one, that's h of 1/2, 1/2. Remember, that was the probability of heads. That was the probability of tails. Now I'm going to stick these into this formula right over here, and I get 1/2 log 1 over 1/2, okay, plus 1/2 log 1 over 1/2. And if I go ahead and I simplify this, remember 1 divided by 1/2 is really 2. So I've got 1/2 log 2 plus 1/2 log 2. Please recall that log base 2 of 2 is 1. So this is just 1/2 times 1 plus 1/2 times 1. That's equal to 1. So the entropy of game number 1 is just 1. Okay, let's consider some other ones here. So I come over here now and I consider what is the entropy of game 2? Well, that's h of 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. This is, remember we said it was a uniform die, it was a fair die. So I come back over here and I again go back to my formula, and it turns out that each one of the individual terms is going to be exactly the same. It's just going to be 1/6 log 6. Remember, the way that I got this 6 over here is a 6. Let me see if this is working. 6 is just equal to 1 divided by 1 over 6. Okay, so I've got 6 of these terms. There's a 1/6 in the front, so 6 times 1/6, those are just going to cancel out, okay? and it is just log base 6. Okay. Now, I could pull out my calculator, and in fact, maybe I'll do that in a moment. But I note a couple of things about, just exactly how big is the number 1 log 6. Well, I note that it's between log 4 and log 8. And remember, we're working in base 2. Log base 2 of 4 is 2. Why? Because 2 to the 2 is 4. Log base 2 of 8 is 3. Why? Because 2 to the third is 8. So I know that log base 2 of 6 is somewhere between 2 and 3. Okay? If I actually wanted to figure that out, I pop up my calculator right here. And the first thing I do is I look for a log base 2, and I don't have it on my calculator. Well, it turns out, and I show this in the next slide, I think, what I can do is I can go, if I want to figure out what log base 6 is, I can come over here and do 6 and take log base 10 of it. And then what I would do is divide it by 2, log base 10 of that. And that comes back, and that's approximately 2.58. Well, that agrees with exactly what I said right over here, that it's somewhere between 2 and 3. If you didn't see this, it's coming up on a slide shortly, and we'll get right back to it. But the point that I do want to make is without even calculating the logs, I knew that this was somewhere between 2 and 3. And so far, what I've established then is that the entropy of game 2 is greater than the entropy of game 1. Okay? Now I come over here and look at the entropy of game 3. The entropy of game 3, remember the probability of heads was 15 over 16. The probability of tails was 1 over 16. So I go ahead and I calculate this entropy, 15 over 16 times log of 1 over 15 over 16 plus 1/16 log of 1 divided by 1/16. So I go ahead and I simplify this, and over here I get 15/16 times log of 16 over 15. Here I get 1/16 times log base 2 of 16. Well, log base 2 of 16, that's nice and easy. That's just 4. 2 to the 4th is 16. So this right term over here just becomes 1/16 times 4, and that's 1/4. Now when I come over here, and again, I'm just trying to avoid using a calculator if I can. There's nothing wrong with calculators. But notice what I'm doing over here is I have a number that's very close to 1, and then I'm taking the logarithm of something that's just slightly bigger than 1. Well, remember, the logarithm of 1, regardless of what base we're talking about, is going to be 0. Okay? So this number right over here is 15/16 times some number that's very close to 0. Okay? And to that, I'm adding 1/4. So I'm just, and again, all I'm doing here is I'm being lazy and I'm trying to avoid the calculator. I'm just saying that h of game 3 is approximately 0.25. Okay? It's probably a little bit bigger, but it's not going to be much bigger. So I come over here and I say h of game 3, which is approximately 0.25, is clearly less than h of game 1, which we figured out to 1. So the conclusion is that h of game 3, which had an entropy approximately 0.25, is less than h of game 1, which is 1, which is less than h of game 2, which was between 2 and 3. So I'm going to play game 3 and I'm going to bet on heads. Game 3 had the least randomness to it. Okay, it had the least entropy. Game 2 had the most. If they were to come back and say, sorry, you can't play game 3, now what do you want to do? You would want to play game 1. You clearly want to bet on wherever there is the least amount of randomness. So I come over here And I go, but my calculator doesn't have LG on it. It doesn't have log base 2. That's okay. You may notice that the calculator I do have had two other bases on it. It had log base 10 over here, and it had ln, which is the natural log, or log base e. I can use either one of these to do the conversion, and the conversion to base 2 is really easy. If I want to do it with base 10, if I want to find log base 2 of x, I just find log base 10 of x and divide it by log base 10 of 2. If I don't have that on my calculator and I only have the natural log, then fine. Then I find the natural log of x and I divide that by the natural log of 2. Either one of these will give you the same answer, and it will be equal to log of x. Okay, so we have some homework. And I say, yes, this counts. I'm going to create a place where you can load it up on Canvas. It's fairly simple. I want to imagine that we have 8 hungry grad students. Who knows? We could be talking about a computer science 667 class in the fall of 2022. And we're trying to decide what food to order. And so our first choice is that we could order pizza. And when we take a poll of the students, 4 of them say that they want onions on the pizza, and 2 of them say that they want mushrooms, and 2 of them say that they want peppers. So suppose we wanted to calculate the entropy of that. Well, we would come over here and we would say that the entropy of pizza would be h of, well, notice there are a total of 8 students here. The probability of onions would be 4 over 8, since 4 out of 8 people want it. The probability of mushrooms would be 2 over 8, because 2 out of 8 people want mushrooms. The probability of peppers would be 2 over 8, because 2 out of 8 students wanted to have peppers. So that's pizza. Now we come over here and we consider another alternative for something to eat. This time it's SOG. And we have to decide, do we want it mild, or do we want it medium, or do we want it hot? And 1 student says that they would like it mild. 5 students say that they would like it medium. And 2 say that they would like it hot. And we come over here, and when we calculate the entropy on SOG, again, what we do is we just make these numbers into probabilities, and we get h of 1/8, 5/8, and 2/8. That is a 2, if you can't tell that. And finally, we come over here, and the other choice is spaghetti. And for spaghetti, there are 2 choices. 5 say they want to have puttanesca. I'd leave it to you to look that up if you don't know the word. And 3 say they want spaghetti Alfredo. So when we come along here, we see that the entropy of spaghetti would be h of 5/8 and 3/8. So I say, which meal has the least entropy? Out of these 3, which one has the least? At this time, you will have to probably resort to your calculators, because I'm looking for actual numeric answers. And you will note here that I say show all work, okay? And this is an actual assignment that I am going to give you. There's going to be a place on Canvas to upload it. And that is just about the end of our tape or video on entropy. More to come.